Hey everyone, thank you all for coming to this lecture today on graphs and sets. My name is Petar Veličković. I'm a senior research scientist at DeepMind, and over the course of today's two lectures, I'll be talking to you about permutation, invariance, and equivariance, and how it relates to processing data that lives on graphs and sets. Before we dive into these topics, I will start by just giving a brief recap of what we already saw in previous lectures. Specifically, you will have seen how to use a small set of guiding principles, such as symmetries, equivariance, invariance, locality, and scale separation. And using those guiding principles, you showed how it was possible to synthesize and steer the design of deep learning architectures, which is potentially quite useful because using such a blueprint, we might be able not only to make sense of all the variety of deep learning architectures being proposed today, but also to reason about and propose any new architectures that you might come across in the future. And the general blueprint that we have derived in this sense concerns a set of kinds of layers, such as equivariant layers, which are in an equivariant way resistant to transformations of a certain symmetry group, and also potentially with the addition of local pooling layers that can help you coarsen the domain if that is required. And finally, as equivariant layers give you answers or outputs for every single element of the domain, and sometimes you care about the answer over the entire domain, we can often put an invariant or so-called global pooling layer at the end, which will aggregate information from the entire domain and give you an answer on the level of the entire domain. And this is just a recap of the building blocks of the geometric deep learning blueprint. So it covers stuff like linear G-equivariant layers that satisfy linearity and satisfy resistance to group action in an equivariant way, no matter which symmetry group transformation G you take, and featurization function X. And the reason why we're okay to stay with linear equivariant layers rather than some more complicated ones is because in deep learning, we typically inject nonlinearities through usage of pointwise nonlinearities, such as sigmoid functions or tanh or ReLU. And when you compose linear G-equivariant layers and nonlinearities, you'll end up with universal approximators over the domain. So therefore, this is a sufficient construction that's employed by most geometric deep learning architectures today. And as mentioned, sometimes it might be useful to coarsen the domain. So go from an initial omega to an omega prime, which is slightly smaller and contains the previous domain within it. And if we need answers on the level of the entire domain, we can use a global pooling layer, which is invariant to the symmetry group transformation. This should all be stuff that you have already seen in previous lectures from Michael, Taco, and Joan. So this slide is mostly there to kind of make sure we're all on the same page as we start to dive into the specifics of the blueprint. And one specific thing you might have seen is that now with this blueprint in hand and with the right choice of a domain to run over and a symmetry group to use, you can actually rederive all of the popular architectures such as CNNs, DeepSets, transformers, LSTMs, graph neural nets, but also you gain access to a wealth of information about all of these neural network architectures that lie in the middle, such as spherical convolutions or mesh convolutions that we will be talking about in more detail as we proceed with the course. So it's a very powerful blueprint, not just for making sense of and unifying everything that you might have seen before in deep learning, but also something that might help you expand your views and reason about the domains that are not necessarily that standard nowadays. And what we'll be focusing on today is showing this geometric blueprint in action. So we're going to deeply dive into how the blueprint works on the domain of graphs and sets. This means we'll be studying models such as graph neural networks or GNNs, deep sets, and transformers. And there's a question here to be answered immediately because, if you start to learn about deep learning, typically the first architectures you will encounter are, multi-layer perceptrons, and then potentially convolutional neural networks or recurrent neural networks, potentially transformers. But all of these have been initially proposed to work on domains such as simple grids, and arguably it's potentially easier to specify a layer like this. But there's a very specific reason why in this course we're going to start by demonstrating the blueprint on graphs. And that is because graphs and sets give us a very nice discrete domain with very small geometric assumptions. We will see exactly what those assumptions are in a bit. And this makes models on graphs and sets very easy to analyze. Like, it's going to be much easier to reason about their properties than when we move on to domains with a bit more geometric constraint. And also, kind of conversely, because if you squint hard enough, literally every domain you'll ever encounter can be seen as a graph. And as a result, pretty much all the architectures we're going to derive in this course can be seen as instances of graph neural networks. So therefore, also from a generality point of view, it makes sense to start with graph neural networks, and then retroactively, as we go through the course, show how many of the existing architectures relate to graph neural networks. And exactly because of this generality, for many, many years, when people thought about geometric deep learning or used the term geometric deep learning, it was nearly synonymous with graph representation learning. So also from a historical perspective, it makes sense to start with something like this. And there is a lot of motivation just in general why we might want to study data that lives on graphs. And that is because graphs are pretty much all around us. In fact, they can be seen as the sort of main modality of data that you can encounter from nature. Because, for example, you have molecular graphs where nodes are atoms and edges are bonds. You can have transportation networks, such as the London Tube map here, and then also social networks, such as the Facebook friendship graph, or even connectome networks in the human brain. So regardless of where you look, it can be seen as the modality of data that nature throws at us is very often graph structured. And besides this, besides the fact that this kind of input comes a lot in nature, it's also coming a lot in various industrial and scientific applications. And as a result, even though they are a fairly recently emerging field, graph neural networks are already affecting the lives of all of us everywhere, in a sense that graph neural networks are already used to discover powerful antibiotics. They are currently used to power food recommendations within social networks like Uber Eats. They are, since quite recently, used to design the latest generation of machine learning chips. So Google AI is using graph neural networks to design optimal layouts for TPU chips. And as a result, many machine learning practitioners will directly reap the benefits of outputs of a graph neural network. And also a project that I was personally involved in within DeepMind, we have used graph neural networks as part of a system that estimates the travel time from point A to point B, which is a very important output that Google Maps can give you. And this system is now deployed worldwide. And compared to the previous baseline machine learning model that Google Maps was using, in some cities, we have improved the travel time estimates by up to a 50% relative increase. So because it's currently serving all queries worldwide, it is basically the outputs of graph neural networks are impacting billions of users and enterprises on a daily basis. So it's certainly a pretty exciting time to be studying graph neural networks. And the fact that graphs occur so often naturalistically is something that's been known to us for a very long time. In fact, here I have the quote from J. Wright Forrester from the 1970s, where he says that all of the image of the world we see around us, which we carry in our head, is nothing but a model. And what this model usually is assumed to be is a bunch of concepts and relationships between them. And based on that, we represent our entire knowledge about the world. And if you look at this concepts and relationships idea, you can see that the graph representation is a very natural way not only to represent data that comes from nature, but also a way to organize data when we're doing reasoning. And as a result, if we do well in graph representation learning, will likely do really well on the path to artificial general intelligence. So also from a general kind of improvement of artificial intelligence standpoint, graph representation learning is likely to be a very important topic. Okay, so hopefully this shows you why it's a good idea to study data that lives on graphs. Now what we're going to do is we're going to discuss how exactly to process data that lives on graphs. But I'm actually going to start with a somewhat simpler domain. I am going to start with graphs that have only nodes and no connections between them. You might know such a structure as an unordered set. There's a few reasons why we're going to start with sets. The first one is it's a simpler domain, so it's going to be much easier to analyze the geometric architectures that arise. Many of the conclusions that we get from sets will naturally carry over to graphs. We just have to incorporate the edges somehow, but most of the math will end up very similar. And even if you restrict yourself completely to processing data on sets, this is still a super relevant area because the modality of data that comes from point clouds or LiDAR sensors is naturally represented as the form of set. And here you can see a demo excerpt from a Waymo video, which shows their self-driving car and how it reasons about the world around it, typically by using these sensors that detect the shape of the surroundings by basically a various number of points which are fed back to the model. So in order to decide how to act in a self-driving vehicle, you need to make sense of this massive collection of points and decide which of these points represent other traffic signals, which of them represent different cars, pedestrians, and so on and so forth, and then use all of this to drive decision making. So even if we completely stay within the realm of sets and don't introduce graphs, we're still solving a potentially very important problem. Okay, so as I said, we're going to assume that we have a graph with no edges. Our domain omega will be just the set of nodes V. And in geometric deep learning, we typically want to deal with featurizing this domain in some way. So we will assume that node I has features xi, which is a real valued vector with k-dimensional features. In the words of our geometric blueprint, this corresponds to our feature space C. So k-dimensional real vectors are the feature space that we'll be using. And once you have these features, a typical way in which you process data like this is you stack the node features into a node feature matrix X, such that the ith row of this node feature matrix corresponds to the features of the ith node. Now, there's one very important thing to note here, in that the very moment you've done this, the very moment you've stacked the node features in some way, you've specified an ordering of the nodes. And what I've said at the beginning is we assume the sets to be completely unordered. So what we kind of naturally want of a neural network that operates on X is that it should not depend on the order of the rows in X. So to kind of very concretely illustrate what we want there, imagine I have an unordered set of 5 nodes, so x1, x2, x3, x4, x5, and the x's are their features. And I want to learn some kind of function, some kind of neural network that will take the features of these individual nodes and give me an output on the level of the entire set that I care about. And what I want of this function f is for it to be resistant to the order in which I fed these features. So in case I completely perturb the order in which I give the set elements, but it's still exactly the same set, I want my function f to give me exactly the same y. And in terms of the geometric deep learning blueprint, this translates to using the n-element permutation group as our symmetry group G, and the different group elements within this symmetry group will be permutations. So the permutation will change the order in which we see the elements in the set, and we want our neural networks to be resistant to this. So it will be useful in order to kind of concretely quantify this. It'll be useful for us to think about what are the operators that change the order of the nodes. And as just mentioned, such operations are known as permutations. And for a set of n elements, there will be n factorial many of them. And what's very fortunate for us is that we can stay completely in the realms of linear algebra when we're talking about permutations, because every n element permutation defines a unique n by n matrix, which is known as a permutation matrix. And such matrices have zeros almost everywhere. They have exactly 1, 1 in every row and column. And the exact positions of the ones are corresponding to the order of the nodes in the permutation. So here you have an example of a permutation matrix for the permutation 2, 4, 1, 3. And here you have exactly in the second, fourth, first, and third column, as you go down the rows, there are ones. And the only effect that this permutation matrix has is that when you left multiply it with a node feature matrix, like the one we talked about before, the only effect is that it's going to permute the rows. So there will be no changes to the features themselves. They will just occur in different positions. And if you remember our previous discussion about group actions row, this permutation matrix is exactly the representation of the group action of the permutation. So I can use this matrix representation to reason about permutations and stay completely in the realms of linear algebra, which is going to make all of the subsequent analysis a lot easier. So now we're ready to invoke the first important part of our geometric blueprint, which is invariance. So what we want is, as I said, functions f of x that operate over these set node features that will not depend on the order of the nodes. Or equivalently, if you apply a permutation matrix to the nodes features, it shouldn't change the result. And this gives us, pretty much by direct application of the geometric deep learning blueprint, permutation invariance as something that's desirable for set neural networks. We say that the set neural network f of x is permutation invariant if no matter what permutation matrix I choose, the result is the same regardless of whether I've applied that permutation matrix or not. So if our neural network f satisfies this property, then we say it is permutation invariant, and it's probably a very useful property to have if we assume that our domain is unordered sets. So you can compare this with our requirement in the graph, in the geometric deep learning blueprint for G invariant layers. And specifically in this case, our F corresponds to the G invariant layer A, and the group action G corresponds to applying a permutation matrix. So there's a one-to-one correspondence with what we said in the blueprint already. Now, there's one very generic way to perform representation learning on sets in a way that's permutation invariant, and it's known as the DeepSets model, which is going to be very important for our discussion in both of the lectures. The way in which it proceeds is it applies a pointwise neural network psi on every single node features in isolation. So typically this psi will be just some multi-layer perceptron applied to every node in isolation. And then what we do in order to guarantee permutation invariance is we sum up the features of all the nodes in the set, and we finally transform that with another MLP phi. And the critical part, which makes this thing permutation invariant, is the sum. Because when I perform a sum of various rows of a matrix, it does not matter in what order I've given the rows of the matrix. I'll always get exactly the same result for every permutation. Another thing that this implies is that you don't have to use the sum aggregation to guarantee permutation invariance. You can use other kinds of aggregators, such as maximization or averaging. And as a result, I will for now stop using the sum operation, and I will use this generic O+ operator. And whenever you see that, you think of anything which is permutation invariant over its arguments. So summing, maximizing, averaging, all of these things work as O+. So the only reason why I'm putting it there is because using sum is not always the best choice, and it's better to think about it in terms of just generic operators, because it allows us to think about these things a bit more broadly. Okay, now permutation invariance, which we just covered, is a great tool if you want outputs on the level of the entire set, but very often we actually want answers not at the level of the entire domain, but at the level of individual nodes in the set. And what this implies is that we would want to still be able to identify node outputs, and this permutation invariant summing would potentially destroy that, or at least make it really hard to recover. So what we want instead are functions that, rather than giving the same answer for two different orders, now it's okay to give different answers for two different orders, but we want to do it in a way that's predictable. We want to do a function that doesn't change the node order as part of running it, which means that if we were to permute the nodes, it does not matter when we do it, before or after applying the function. And this gives us, once again, a direct application of the geometric deep learning blueprint, the notion of permutation equivariance, where we say that a function f of x is permutation equivariant if no matter what permutation matrix I choose, it doesn't matter if I apply it at the input level or the output level, I will still get exactly the same results. And the reason why we're now doing a capital boldface f is because the output of such a function, in order for this kind of linear algebra writing to make sense in the first place, it now has to return a matrix rather than a vector. So we're using the capital boldface f just to make it super clear that the function is taking a matrix and returning another matrix also of node features. And as mentioned, you can look at this formula for a little bit and compare it against what our requirements in the geometric deep learning blueprint are. And you can see that our G equivariant layer B matches very nicely with this F, and the group action G once again corresponds to a permutation. So far so good. We have been able to derive the two key elements of our geometric blueprint, invariance and equivariance, on the specific case of sets. And we saw how it very naturally relates to the kind of constraints we would expect of a neural network that processes things on sets. But as discussed in previous lectures, strict resistance to symmetries is not the only thing that we want. We also want our neural network's predictions not to completely blow up when we do something which is not quite a symmetry transformation, but instead distorts the input a little bit. So, and that's because nature usually doesn't transform data in a purely symmetric way. Very often when we observe information from nature, there will be some level of noise just associated with our measurement. And we want our neural network to not look at this noise and go completely haywire. Like, we want the predictions to still be stable. And if you recall the previous lectures, particularly the ones regarding scale separation, we have derived that it is super useful if you want to obtain this level of resistance. It is super useful to compose local operations to model large scale ones, because if you have an operation that's totally local, then any errors will not be globally propagated. And this is why, for example, when you build convolutional neural networks, very often you build them with very small kernels, like 3 by 3, but make them super deep. Similarly, what we would want also of our set and eventually graph neural networks is for the layers to be local with respect to the structure of the domain. And we can now ask ourselves the question, what does it mean for an equivariant layer on sets to be local? Well, there's one very obvious way we can enforce locality in set functions. We just have a shared function and we apply it to every node's features in isolation. So in this case, we have hi, the latent features of a particular node, which are computed as a result of applying a function psi on that node's features, and that's it. Like, we just have one function and we apply it on every node in isolation. And then if we want to like explicitly write out the permutation equivariant function that results as a result of this, we can just stack these hi's in the same order in which we stacked the original x's. And this gives us a matrix H, which is considered to be the output of our function f. Okay, so this seems like a very simple and natural way to enforce our equivariant layer to be local. Just stay within that one node you're in and don't go anywhere else. And in fact, if we recall the general formulation of DeepSets, we can see that it very closely follows what our geometric deep learning blueprint would have us construct, because we have this pointwise function, which corresponds exactly to a local equivariant function over sets. And then just in case we're interested in predicting something on the level of the entire set, we can stick a global pooling tail at the very end. So this permutation invariant aggregator with phi is something that you stick at the very end of the architecture if by any chance you're interested in predictions on the set level rather than the node level. And if you think long and hard enough, you might end up realizing that this is actually as far as we can get with sets, probably, because anything else, like any kind of more broad layer psi that would act on individual nodes and potentially consider some other nodes, if you wanted to keep it local, you would have to assume some kinds of relationships between your nodes. And we said upfront, our assumption when we're dealing with sets data is that there are absolutely no additional edges, no additional structure in this domain. So we're just thinking of it as a completely isolated set of elements. And as a result, this is probably the best and most general possible form of a neural network that operates on sets. So this is a very important point, because directly by following the prescriptions of the geometric deep learning blueprint and just by intuitively reasoning about what it means for something over sets to be permutation, equivariant, and invariant, we have derived exactly the most generic set neural network and related it directly to the blueprint. And this is something that just goes to show how powerful the blueprint can be on a wide variety of domains. But we're not here to study just learning on sets. The graphs are the main show event for today. So I think that now that we've demonstrated invariance, equivariance, and locality over sets, now we can think about how do we generalize all those terms in the sense when we don't just have a set of nodes, but we also have a set of edges between them. And that means we will consider graphs G, which are usually represented as a tuple of nodes V and edges E, where the set of edges E is just a subset of the Cartesian product with the nodes and themselves. So it specifies which pairs of nodes are connected in this graph structure. And there's many, many ways in which you can represent the edges within a graph. And because I want to stay within the realms of linear algebra, that's going to be the easiest for all of us to follow these notions of invariance and equivariance as before. I'm actually going to use a matrix representation for the edges. So you might have come across the adjacency matrix before. It is, in our case, just going to be a binary matrix that gives you 0 or 1 entries dependent on whether or not a particular edge is inside the graph. And I apologize, there's an error on this slide. The 1 and the 0 somehow ended up flipped. So it should be a 1 if I and j are in the graph and 0 otherwise. And basically, this matrix A is of shape number of nodes times number of nodes. And it's, in our case, just a binary matrix that tells us which of these pairs of nodes are connected. And one very important thing to note here is that by doing this, edges have now become a part of the domain. And any further additions like edge features or edge weights or something like this are possible. They're very much possible, especially if you're doing things like computational chemistry. But just for the sake of keeping the math as simple as possible, I will be ignoring them for now, at least until the second lecture today. Now, that doesn't mean that I'm making the problem any simpler. Most of the mathematical constructions we will derive with a simple binary adjacency structure will carry over to the cases where we have edge features or anything like this. So for now, we'll just stay in this realm of every edge is just a binary indicator of whether or not two nodes are connected. So one thing that's very important to note is that if we don't assume any additional geometry, the main desiderata we had on sets, so we wanted our set neural networks to be resistant to permutations through permutation, invariance, and equivariance. It is actually exactly the same on graphs. We also want our graph neural networks to be resistant to permutations of the nodes and edges inside the graph. So what's changed? Here I've just brought back the previous desiderata we had on sets, like we want our set neural network to give us the same output regardless of how I permute the order of the nodes. And well, The only thing that's really changed in the case of graphs is that now I assume there's some connectivity structure between my nodes. And therefore, when I permute my nodes, I also must permute my edges in exactly the same way. So here, if you stare hard enough at the two graphs that I've given at the bottom, you will see that they're actually exactly the same graph. I just chose to present it in slightly different ways. It is what we call in graph theory as two isomorphic graphs. And as a result, we want our permutation invariant graph neural network to still be resistant to something like this. Okay, so the main difference then is that any permutation that we apply on the node features now must also accordingly act on the edges, that is the adjacency matrix. And if I told you that the adjacency matrix is of the shape number of nodes times number of nodes, then permuting the nodes corresponds to permuting both the rows and the columns of the adjacency matrix. And that means that if I'm using a permutation matrix P to permute my nodes, that means I'm permuting my adjacency as PAP transposed. The first P is responsible for permuting the rows. The P transpose is responsible for permuting the columns. And you plug this additional part as input to your functions, because now edges are a non-trivial part of the domain, and therefore any function over them must be mindful of them. And we recover basically the same rules as we had for sets. So our graph neural network is permutation invariant if no matter how I permute the nodes and edges, as long as it's done consistently, I should get exactly the same results. For permutation equivariance, regardless of which permutation matrix I choose, it shouldn't matter whether I've applied the permutation matrix before or after applying my function. So the only different thing now is that we have the adjacency matrix A as an extra input to the function, and we transform it in a slightly different way than we transform X. But in all other senses, these two concepts carry over very naturally from sets. But okay, invariance and equivariance carry over straightforwardly. One thing which carries over in a slightly more generic fashion is locality. So as mentioned before, on sets, we started off by assuming no structure, no relationships between the different nodes. On graphs, we actually have a slightly broader context, which is a node's neighborhood. And that means we don't have to transform every node just in isolation. So for a node I, we can derive, for example, its one-hop neighborhood, often denoted by Ni, as the set of all nodes J, which are connected to I with an edge. And once you have a set of neighboring nodes, you can also extract a set of neighbor features, X and I, which is just this multiset of the X vectors for all the nodes that are in my neighborhood. And now I can do something more generic than just having a pointwise local function. I can have a local function that operates over not just the node itself, but also all the features in its neighborhood. And this local function we will call phi. And once we have a local function phi like this, we can actually construct permutation equivariant functions by just, as we did for sets really, apply this phi on every single node, in this case its neighborhood, in isolation, and then stack the results into a new node feature matrix. Now, if you want to ensure that this thing is equivariant, we need to do just one more thing, because now our local function phi takes as its input a set. Capital X and I is a set of all the neighbor features. And as a result, we want to be resistant to the exact order in which we feed the neighbors of that set. And therefore, phi should be designed to be permutation invariant. That is, if we can guarantee that phi is permutation invariant, we can guarantee that capital F will be permutation equivariant. And I think it's a very useful exercise to prove this, and I will leave this for you to do after the lecture. I very much recommend you do this. It's a great way to check that you fully understood the concepts behind permutation invariance and equivariance, especially on graphs. And I do realize that doing all of these things with math for so many slides might potentially muddy the waters a little bit, because every single step of the way. The concepts might have made sense, but I've introduced a lot of new notation. So I thought now is a pretty good time to take a brief pause and just take a look visually at everything we've done so far in the domain of graphs. So we have defined our permutation equivariant functions on graphs as built using a local permutation invariant function phi, which acts on a particular node and all the features of the nodes in its neighborhood. So in this case, for node B, the neighbors will be A, B, C, D, and E. We often add the node itself to its neighborhood. It just gives extra context. And based on this entire set of features and the features of the node itself, which gives a nice sort of skip connection, the graph neural network computes new features for that particular node, HB in this case. And now what you do is you apply this function phi separately in parallel to every node's neighborhood, obtaining the H vectors for every other node. Note, I haven't told you yet how to build phi, and this is going to be a very exciting part of this lecture series in general. But for now, just the point that I want you to remember is that if I have a permutation invariant local function phi that acts on the set of all of my neighbors in the graph, then I can apply that phi to every neighborhood in isolation to construct permutation equivariant graph neural networks. And this is a very, very, very common way to build graph neural networks. But before diving into the specifics of that layer, I just want to take a step back and look at the broad geometric deep learning blueprint and see how we can use what we just did, like how we can use the this graph neural network layer that we just derived to do meaningful tasks over graphs. So imagine I give you a graph with input features x, such that xi are the features of node I, and some adjacency structure, which just for convenience, I will encapsulate within an adjacency matrix A. After I run a graph neural network over this, I will update my features from the x's to the h's, and I will do so in a way that depends on the node's local neighborhoods, so all the features of the nodes that are in the vicinity. The adjacency structure typically doesn't change as a result of applying this GNN layer, but we will discuss some interesting ways to modulate the graph structure for the second lecture today. But for now, we assume that A always stays the same. It's just the node features that change. And once you have this, you can do all sorts of interesting tasks on a graph. If you're interested in classifying individual nodes, you can learn a classifier on the individual node features to predict any node level outputs that you might care about. If you're interested in classifying entire graphs, this is now a prediction on the level of the entire domain. So thinking back to the geometric blueprint, what you need to do is you need to somehow transform your node features in a permutation invariant way. And as we've seen in DeepSets, one very simple way to do that is to just, for example, sum up or otherwise aggregate the individual HI vectors, and then learn a graph classifier over the aggregated feature vector. There's one very interesting thing that comes up in graphs and doesn't come up in sets. And that is because now edges are an important part of our domain, we can also have prediction tasks over edges. So edge classification and edge regression are totally possible. And a very common instance actually predicts whether or not an edge should exist between these two nodes at all, which is a task known as link prediction. And under certain circumstances and GNN architectures, you can set up an edge classifier or link predictor as some function that considers the features of the sender and the receiver node, so HI and HJ for an edge IJ, and potentially any edge features you might have between them. And based on these information, your classifier will predict, for example, a 0, 1 as to whether or not that edge should exist, or maybe some other property about this edge. Now, we've just covered a lot of ground and came up with this generic graph neural network architecture and related it pretty much all the way to instances of the geometric deep learning blueprint. So it's a great validation that the blueprint makes sense in these two domains. But there's one thing that I haven't told you much about, and it's going to be pretty much the main thing you need to know if you want to work on graph representation learning. And that is this local permutation invariant function phi. I've sort of just mentioned it, and I said that it's something that we will need to build, and that will specify everything else in terms of permutation equivariance. And actually, in common lingo, we might refer to this function f as a GNN layer, but this phi, depending on which literature you read, can be called diffusion, propagation, message passing. And it's, in my opinion, one of the most intense areas of research, how to build good candidates for phi. And while there is a lot of research being put out every single day proposing various kinds of phis, what we have synthesized and discovered as part of writing our proto book is that, very fortunately for us, almost all of these phis, at least 95% of them, can be classified across 3 spatial flavors of graph neural networks, okay? And this is probably going to be a very useful tool, these 3 flavors, as you start to navigate the field more. And here is a bird's eye view of the 3 flavors. So you have convolutional graph neural networks, attentional graph neural networks, and message passing graph neural networks. I will go through them one at a time. Here I've just given kind of a pictorial representation of all of them, along with the equations for computing the HI based on the neighboring xi's. But one thing that's very important to note is that as you go from left to right, the space of functions that you can represent grows. So you can represent convolutional layers as a special case of attentional layers, and you can represent attentional layers as a special case of message passing layers. And that typically means the further right you go, you can fit more interesting or more complex kinds of problems, but there is a cost to scalability, and there is a cost potentially to overfitting that you must take into account. So it's a bit of a trade-off as to which exact flavor you'll end up choosing. So on that note, let's start with convolutional graph neural networks. And they realized that it's a big problem to decide exactly how to aggregate all of these neighbors in the neighborhood, because for every node, the neighborhood could have a completely different size. So you cannot really be pragmatic that much about some size-dependent filters or something like that. So what the convolutional GNNs do is they just upfront say, I'm going to say, this is how much a particular neighbor is important to me, and those will be specified in terms of these fixed weights, Cij. And what I'm going to do is I'm going to pointwise transform all of my node features, just like we did in DeepSets. And then every node will compute a weighted combination of all of its neighbors based on these C coefficients. So you basically compute, for example, a sum of all of your neighbors, where each neighbor is multiplied by the corresponding weight. And the key part is that these weights are specified in advance before you ever apply the graph neural network. And typically, this is done in a way that directly depends on the adjacency matrix. For example, Cij can be 1 divided by the degree of the node j, and as a result, it will compute the average over all of the neighbors. Some popular instances of these kinds of layers include Chebyshev networks, the graph convolutional network of Kiff and Welling, which is currently the top-cited graph neural network paper, and the simplified graph convolution, or SGC, which has shown just how simple these layers can get, and you can still recover a lot of the benefits for many graphs you encounter in the wild. So because they upfront specify the weights, and they're usually some function of the graph topology, these kinds of models are super useful when your graphs are homophilous. That is, when your edges encode label similarity. So if an edge between A and B says that A and B should likely share the same label, then this kind of averaging approach is actually a pretty good regularizer. It basically robustifies your features based on the features of all of your neighbors, and therefore you're more likely to share the same label with the majority of your neighbors. And because the coefficients are specified up front, this equation for computing HI can be computed very efficiently as a sparse matrix multiplication, which makes it highly scalable. And actually, most industrial applications of graph neural networks on really large graphs, so for companies such as Pinterest, Uber Eats, and so on, these applications will typically use convolutional graph neural networks. Now, sometimes it is not enough to pre-specify a coefficient of interaction, and it's certainly not appropriate to take the average of all of your neighbors, because links don't necessarily have to encode label similarity. For example, if I am a member of a social network such as Twitter, and I retweet, I share somebody's post on Twitter, this does not mean that I agree with that person necessarily. In fact, I could be strictly disagreeing with that person. So giving me the same label as that person is not necessarily the right way to go. And there exist more complex graph neural network architectures that explicitly try to take into account the fact that different neighbors could be valued differently, and this could be done in a feature-dependent manner rather than a pure graph topology-related manner. And one very natural way to do this is by using an attention mechanism. So what happens here is that previously for convolutional graph nets, you had a fixed coefficient of interaction. Now this coefficient of interaction is computed based on the features of the sender and the receiver node. So we've replaced the Cij constant with an attention function that takes features of xi and xj and produces a scalar that we often call alpha ij. And there's a few very popular models that try to deploy attention style ideas within the graph domain. Some special cases include the mixture model CNNs or Monets, the graph attention network, which we have proposed at iClear 2018, and a more recent improvement to the graph attention mechanism, the so-called GATV2, which fixes the static attention problem in graph attention networks. And you can see how such an approach is a potentially very useful middle ground, because it allows you now to learn a different amount of interaction you want from every one of your neighbors, and therefore you no longer require the edges to encode for homophily. But you're still only computing just one scalar per edge, so there's not a lot of scalability cost associated with this. Once you compute the features, it is still just, once you compute these scalars, it's once again just a sparse matrix multiply. And as a result, these kinds of attentional models tend to be quite popular as a middle ground, where you do expect some kind of complex behavior along your edges, but you still do it in a way which doesn't completely require the full firepower of message passing, which might be harder to scale. And we will see in the second lecture how it's exactly in this space where some of the most popular machine learning models nowadays live, including the transformer. And finally, in the most generic form of graph neural network layer, which is the message passing graph neural network, we can actually compute arbitrary vectors, so-called message vectors, to be sent across edges. So note that in the previous layers, like the convolutional and attentional, we still computed something in our neighbor, and then we aggregated that in a weighted combination. Now, it's not just the neighbor that decides what gets aggregated, it's also the receiver that is asked. So we replaced the previous psi function that acted only on the xi nodes with a psi function that acts on both the sender and the receiver node, and they collaborate together to compute a message vector, mij, which then the receiver node aggregates in some permutation invariant way. There's a lot of popular layers that propose message passing computation, interaction networks, message passing neural networks or MPNNs, and DeepMind's graph nets, which we will study in more detail later today, are three specific instances that you might want to take a look at. Now, in terms of one-hop spatial GNNs, this is the most generic layer you can have. And it no longer assumes that your edges encode for certain weighted combinations that need to be computed. Edges just give you a recipe to pass data, and the message function decides what is the actual data that needs to get passed. As a result, they're a bit harder to interpret, they're a bit harder to scale up, and they might be a bit harder to learn because there's a lot more parameters within this psi than there used to be, and there's a lot more incoming signal that the receiver node has to deal with. But because of that kind of expressive power, they are the ideal choice if you want to do computational chemistry, reasoning tasks, or simulation tasks, because those kinds of tasks actually necessitate edges as a recipe for passing messages. And this actually covers the last part of the first lecture that I want to go through with you today. So I'll just do a quick recap of what we have done. We've looked at how this geometric deep learning blueprint that you've seen in an abstract way over the previous lectures can be specifically applied to the domain of sets and graphs. And within this domain, we came up with the key notions of permutation, invariance, and equivariance that we typically want all set neural networks or graph neural networks to satisfy. And then we found that on the level of set neural networks, the DeepSets model can be seen as a universal blueprint, which very naturally follows our geometric blueprint. And then we studied various permutation equivariant layers for graphs, the so-called GNN layers, and how they are used both scientifically and industrially. And perhaps most importantly, in order to navigate the field better, we have came up with this 3-flavor categorization of graph neural network layers into convolutional, attentional, and message passing layers. And another exercise that I think would be very useful for you to complete over the next few days, just to verify that you understand the representational containment of these models, is prove that you can use an attentional graph neural network to represent a convolutional one, and that you can use a message passing graph neural network to represent an attentional one, therefore showing that there is a containment. So the set of functions representable by convolutional GNNs is less than or equal to the one representable by attentional, and less than or equal to the ones representable by message passing. And to give you a taster of what's to come later today, we will try to lift as many restrictions we had before as possible. So we're going to stop assuming we don't have edge features. We're going to also incorporate some kinds of graph features. And we're going to really dive into how complicated this message passing system can get through a detailed implementational view of the GraphNets model that was proposed by DeepMind and represents one of the most generic forms of spatial GNNs. Then once we cover that, we will see how we can connect graph neural networks to first the DeepSets model that we saw before, and then also the transformer model, which for now I've only hinted is sort of related to graph neural networks, but I haven't yet said exactly how that relation will happen. And later today, we will make that connection very clear. Then we will attack one of the main assumptions that we had all along, which is that the graph is given to us. And actually, unfortunately, very often nature is not kind enough to give us a graph. So we will talk about latent graph inference as a very important emerging area for doing machine learning on graphs when there is no graph. And lastly, time permitting, we will talk at length about how can we quantify the expressive power of graph neural networks and what are the things they can do and the things they cannot do. And it turns out that the perspective of graph isomorphism testing will be a very important one for doing this. And as a result, we'll have a detailed discussion on isomorphism testing and how it relates to graph neural networks. And something that we won't cover today, but will be touched upon by Joan in the upcoming lecture on grids, is how we can approach graph neural networks from a spectral angle and derive a graph version of a Fourier transform, which might let us talk about a more broader set of graph neural network architectures than the simple 3-flavor view that we had here. So this was my last slide for the first lecture, and I believe we have about 7 minutes for any questions from the audience. So thank you very much, and I look forward to discussing with you.
Yeah, thank you very much, Peter, for the interesting lecture. So I think there are a few questions in the chat. We could take them first. Then more would come from campus-wide as well.
Sounds good. Okay, so I'll just start by addressing the questions in the chat then. So first of all, yeah, great to meet you too, Lekan. The next question was from Yama. What about if the graph is extremely big? How will the permutation variant operation affect the learning process, given that we have limited resources? And actually, immediately afterwards, the person suggests that maybe we just have to sample nodes, which brings another question on the best way of sampling. And in a way, you've just done both sides of the conversation, because yes, when the graph is extremely big, you actually do need somehow to make the graph smaller before you can run the graph neural network on it. Otherwise, you will run out of memory. And most popular approaches in industry that apply graph nets over these like millions or billion node graphs actually first subsample the graph. So when you have to make a prediction in a node, rather than using the entire graph to make a prediction in that node, you subsample some tiny patch around that graph, and you run a graph neural network over that patch. And that's typically how you do it. I would recommend reading the GraphSage paper, which unfortunately I did not have space in the lectures today to to cover. Basically, it just samples uniformly at random some neighbors, and then some neighbors' neighbors, and then uses that as the graph over which you will do your computations to compute the answer for the central node. And in most cases, that actually works extremely well. But there is a lot. It's a super booming area of research on the best way to do sampling. Some approaches you might want to look at include fast GCN, GraphSaint, Ladies. Yeah, the method is actually called Ladies. I will share some papers in Campus Wire later on, so you can take a look. But yeah, it's a very important question. Unfortunately, not one we had a lot of time to cover today. But yeah, thanks for asking. It's a very important one. Then I see there is a question from Idris, and I want to be sure that I understand the question correctly. So Idris, could you unmute yourself and ask the question, please?
I think it's about one of the slides where you showed how a message is propagated. So the initial node features the X and the propagated H, the line representation H. Yeah, so we wanted to know the difference between the two.
Mm-hmm. Yes. So you can think. Mm-hmm. Sorry. Yeah. Okay. So basically, the X's are the input features for your nodes, like whatever features you have given to you at the input stage, and then the H's are a latent vector. So they are just some representation of that node based on the initial X, and also all the X's around that particular node. So basically, the X you can think of as the input layer of the neural network, and H as a latent or hidden layer of the neural network. Like it's well, what comes out of a hidden layer of a neural network. And then you can take those H's and transform them again to some new H's and so on. You can make very deep neural networks in this way. And then finally, when you're done processing, you can run a classifier on top of the H's, as we said before, to say classify individual nodes or classify entire graphs. Does that answer your question, Idris? Yeah, sounds good.
Yeah, it's okay. Thank you very much.
Perfect. No worries. No worries. So yeah, this once again, the question from Jama is self-answering and a very important one. We could say everything is message passing, and I very much invite you to do the exercise that I suggested at the end to show that you can represent convolutional and attentional as message passing as well. And in fact, yes, so all of these layers are just special cases of message passing, and anything we'll ever see will be just special cases of message passing. But the reason why we categorize them in this way is because the exact way in which you do the message passing can impact a lot the implementation cost and the learning complexity and the number of parameters you're going to have and the kinds of functions you can represent. So it is actually quite meaningful partly because the graphs domain is a bit more irregular and generic than, say, the image domain. It actually makes sense to have different kinds of message passing flavors for different kinds of graph structures that you're expecting. For example, convolutional graph neural networks are really useful if you expect your edges to just tell you, hey, this neighbor of mine should share the same label as I do. Then if you just take the averages over your neighbors, you do all you want. And you do that in a way that's really easily implementable because it's just a sparse matrix product. Whereas the full message passing layer requires you to do gathers, scatters, edge level vector messages. It's much more complicated to compute in an efficient way. So that's the reason why we have this categorization. I hope that answers your question, Jama. Was that okay? I think you're still muted, but yeah. Great, thank you. And finally, there was a question on what about coarsening? We are actually not going to talk about coarsening on graphs at all for these two lectures. There's a very important reason for that, and that is I don't think we yet have coarsening layers that actually improve significantly over GraphNets that don't have them. So if I start talking about coarsening layers, I will end up talking a lot about something you probably will not find useful in the near future. So there is a huge body of literature about pooling layers in graph neural networks, diff pool, graclus, and these kinds of things that either use the features to decide how to coarsen the graph or use the graph topology to decide how to coarsen the graph. So you might say there are some cliques or something in the graph that you might want to aggregate in a hard way, just like in images, you pre-specify which patches of the graph you're going to pool on. So it's definitely possible. There's a lot of really cool research going on there, but I made the conscious choice to not talk about it here because of the time constraints and because I wanted to give you something that's going to be immediately useful for the kind of data we have these days. So I will definitely share some references on CampusWire, but thanks for asking. It is definitely a very important part. Okay, I think we might have time maybe for one more question taken online.
Hi,
I still
Peter.
need to, yeah, yes, hello.
About this question, coarsening,
Mhm.
you mean no need for it in the graph or?
So yeah, specifically for coarsening graphs, there are many methods being proposed, such as diff pool or clique pooling or graclus, which will decide for you how to coarsen the graph domain to a more sparse domain. But I am not covering them in these lectures because, at least for the data we have right now, they're not really giving any significant benefits to just doing a bunch of equivariant layers and invariant at the end. So
Okay,
yeah.
because it is very important for break the curse of dimensionality on the last section.
Yes, exactly. Like, it is in theory very important. In practice for graphs, it hasn't shown to be as important yet. That's the main reason why.
Okay, about also nonlinearity, assume it in the pi, the local function. Or
Yeah, so I didn't put, yeah, I did
Yeah,
not put
example.
nonlinearities because they're kind of like, you can put them as part of the psi and phi functions, but yes, ReLU is what you would typically use in all of these layers. Yeah,
Thank you.
no worries. Thanks for asking.
Yeah, so
okay, so
I have a question about the attention in this case. Is it a way to look at the signals coming from the node features and say that probably this one is strong enough, or we are just looking at how much they affect the output each time we have these specific nodes?
So yeah, that's a very good question. And I think attention can be seen as a way to model the influence between the different nodes. So like, how much is this particular neighbor important for your particular prediction? And like, we will dive into attention a bit more in the second lecture. But yeah, like, definitely you can look at it as a way of computing influence levels. And even in some cases, it can help you figure out what the graph is if you don't know what the graph is. But I'm skipping ahead. You will see that in a few hours.
Okay, great. Thank you. But I think there's one more question on CampusWire. I don't know if you would like to take it live or you would check it out on CampusWire. But it's up. Okay.
Okay, yeah, I'll quickly say, okay, so there's a question of how can we use this to model dynamical systems in MDP in the setting of RL. There are a lot of very exciting ways to do that, and I will share a lot of cool references on using GraphNets for RL in CampusWire. I think explaining them in detail will take a bit too much time for this question session, but it's a great question. I will put the answer for sure. Yeah.
Okay, great. Thank you very much, Peter, and see you soon.
Yeah, see you in an hour, everyone. I hope you enjoyed it.
Yeah, very well. See you, bye.